Just try to dial that in. Interesting to be at a automation conference and even the computerized display system is giving us trouble. But that's very good, helpful thing to happen before I give this kind of talk. So my thing specifically is I'm out in Saskatchewan, in Saskatoon. If anybody's been here, give me a hands up or something because nobody visits us really. Nice, nice. We do exist, and I have a very nice Hamilton that I'll hopefully be able to show you. I don't know if Nicholas Gold is in the room, but he should be envious of it, and he's got a very nice one here. Okay, I'm at a bit of an angle. Sorry to see my slides. So I like to move around when I talk. I'm supposed to stay here for this presentation because of the camera, but basically, I'm going to summarize what I'm going to talk about in a simple way, where there's a problem in a lot of stuff to do with automation, and anybody who's entry level coming into automation, this is going to be very, very obvious, and anybody who's actually doing the technical work is going to be excruciating obvious. But to put it bluntly, on the left is a coffee maker. I like the coffee that it makes, but I hate the coffee maker because I'm the first one in every day, and I have to fix it every single time, and it's never the same error. The thing has to have beans in the back, and it can only use filtered water. It's got a little, I call it like its diaper on the bottom, where it like dumps the spent grounds into like a little pellet. And if any of these things go wrong, it turns on a tiny little red light at the top that I can't see because it's a tiny red light on a black background. And I'm very, very colorblind. I have 12% perception of the color red. So I'm fundamentally screwed at repairing that machine. And you'll notice a coffee machine, it's a liquid handler. And it's black and it's silver, and so is my other one. One of them is less maintenance than the other, and I'll let you guess which one is that way. So I've summarized kind of this in some, the words at the bottom here are basically a reminder for me why the heck I have any slide up. The question, firstly, though, is a coffee maker is not rocket science. They've been around for like 1,000 years in my mind. So why does it have to be so hard? Secondly, why does it have to have so many problems? Shouldn't it be able to tell me it's going to have a problem, then I can prevent it? And then the last one is, why do the fixes and the setups have to be so slow? And I won't snipe out any particular company with the way they've designed their IDE because Mike is here in the room. But and he can't control it, and I think he's got sympathy. I like it now, but I mean, to be fair. But anyways, a former individual that was involved here in Montreal, Ben Scott, is now my boss. And his call was not to personally get down to the lab to deal with this himself because he's in Toronto and the lab's in Saskatoon. So he hired me. So my background here, I basically stayed in Saskatoon for most of my career. I was very lucky to be able to do that. I didn't put years on here, so you can kind of guess at my age, but my comments here might be a bit revealing. I worked in the cancer cluster ages and ages ago doing my honors project. I was the first student at the U of S to do a CRISPR-Cas9 project. It kind of worked, but it was a good example in troubleshooting. The next thing I did is I did a project in nutrition, aging, genome topology. Don't know if anyone's familiar with that, but I used a technique called 3C, chromosome conformation capture. It's for looking at genome topology. At the time that I did it, the only people that were doing it were Oxford, Cambridge, and a handful of Bay Area labs. The prof that I was working under, he was Oxford, Cambridge trained. So he brought this demon over here. One of my committee members read that in the title of my your entry talking to a master's, and he dropped off my committee and he said my project was impossible. It wasn't. I got it done, but it was pretty painful. After wrapping up my master's, I went to a brewery, and so a lot of stuff in the automation world that we talk about is what would you call it? Bioreactors. Making beer, it's a bioreactor. It's just I like the product more. So that's good. And we're pretty good at beer in Saskatoon. I want to steal LRIG and have it be in Saskatoon at some point in the future. We have a pub there, Winston's, 96 different taps of beer. That's a lot of microbiology had to happen to make that possible. That feels very LRIG. Yeah, so I had some time at that brewery and I designed a PhD project while I was there. I think that student has just finished it in the last like 3-4 months, but it was a yeast systems biology project where we actually wanted to see if we can tune these very large scale bioreactors using some of these almost ancestral brewing strains of yeast, if we could optimize their performance so they'd brew much faster. In the time period while I was there, we took a lot of our brews from I think one of the flagship beers was every 40 days they were turning around a batch. The first year I was there, we got that down to 21 days. And then by the end, I think the best I could do was 17 because when you're doing 1,300 liter bioreactors, it's a little different than a Falcon tube or whatever size you'd be doing it in. After I left that, I went over to BASF. Everyone I assume knows who BASF is. They're world's biggest chemical company. They're the pioneer of the Haber-Bosch process. They're the reason why we have fertilizer for a lot of cases. I worked for them, and they're very methodical and they're very, very obsessive. So within the first weeks of me being there, they forced me to take every single process efficiency kind of thing that exists in the ecosystem, every methodology, Lean Six Sigma, Kanban, anything you can name, we had to take it. And we did that for our quality assurance for canola and wheat, where we were trying to maintain the genetic integrity and look at the changes that were coming out of the lab and the supply chain. I think that's about all I'll say there. Oh, and that was my first interaction with robots. I don't know if Dave is here from TCAN, but I had a TCAN Evo. Pretty good, pretty straightforward. Can't do anything crazy advanced on those guys, but not too bad. And then after that, I came over to GIFS, and GIFS is also in Saskatoon. Oh, I forgot I've got some nice pictures. All those beers there, all those different colors you see, I made every one of those. That was a lot of fun. And the other last one I'll mention is, forgot to say this going through it, but in my master's, I was assigned a very, very long series of colored assays where we were using RFP and GFP. And he knew I was colorblind and he still assigned it. But luckily, there was a Japanese exchange program happening for a week. And so I had a Japanese exchange student come and she pointed at yellow and green for about 3 days. And we got through it. So that was pretty good. And then my two robots over here. So I've got, in my building, I've got 4 Hamilton Stars and one very, very maxed out Vantage. It's got all the bells and whistles and we are very happy to have it. So very brief thing about where the heck I come from, because I'm sure my suspicion is not many people here as I've have gone further left on a world map than, I don't know, Ontario. So I'm out in Saskatoon. The interesting thing you can see on this map to the right, so the main highlight here where all those lines are pointing, that's the core university campus. We have a massive campus, there's 26,000 students there daily, but there's about 50,000 people on and off campus every single day. Saskatoon is about 300,000 people. That's a sixth of the city is on campus every day. It's a very big university city. GIFS, there's my front doors on the top left. Boffin's Garden is where I can go to eat lunch. It's a Japanese style, gorgeous garden, very, very well curated. We've also got a Canadian light source, and we've also got the Vaccine and Infectious Diseases Organization. I think we're the only synchrotron in Canada, and I think we're the only vaccine and infectious diseases place in Canada. Those are all within a block of me. So Saskatoon, not quite as irrelevant maybe as I would think most people would see it. We also have massive facilities from big companies there, BASF, Bayer, Nutrien. If you don't know who Nutrien is, there's already a couple of people here I've told them about. That's the world's biggest potash producer. If you like food, you should really care about that company. And then 7 Shifts, which is anyone who's done work in a bar or anything. 7 Shifts is used to organize shifts, and Collabs is another kind of comp sci engagement group. So we do have quite a bit going on in Saskatoon, but specifically the Global Institute for Food Security. I'm always reading this at a bit of an angle. The vision here, a world where everyone has access to safe and nutritious food. And then our mission statement is that we want to work with partners to discover, develop, and deliver innovative food solutions for the production of globally sustainable food. It's a bit of a long statement, but it's a very important mission. And to kind of zoom in on this a bit, we have a lot of platforms at my institute. I'm the engineering biology platform. We're the only engineering biology platform dedicated purely to food security. And this includes a lot of things that like enhancing supply chain resiliency and domestic biomanufacturing, things that we'd love to get going. We have a lot of opportunities in Saskatchewan with how much crop waste we have to valorize a lot of products, which is the last point here. And the other thing that's vital is because we care about the food chain, we're looking at things like protecting Canadian crops and livestock. I don't know how much agricultural background anyone has here. I had barely none before I worked for BASF. There's a lot of terrible diseases that run through crops like Fusarium head blight on wheat, clubroot on canola, Chickens have quite a few ailments that we need legitimate and quick cures for, and we need kind of a bioengineering approach to rapidly solve these problems as they evolve out of the ecosystems. So I have the great benefit of being in engineering biology that nobody ever comes to us with a normal problem. It's always a little bit weird. So the top left is kind of a standard case of some of the things we've done. Pretty simple. We're stamping out a bunch of E. coli transformations onto a plate. This is both to check how accurately our Hamilton is pipetting, but also can we transform at high throughput? This was something I did just a few months after starting this position. Some other assays we're looking at is a growth curve Bayes assay, where we're going to look at the delta value between two different strains to see if the enzyme of interest we put in them is actually helping them grow faster. By proxying the success of an enzyme to growth, kind of using a little bit of a complicated mindset, we can do these very, very simple high throughput assays to quickly check if some of our engineered enzymes are performing better. Won't get into the details of that purely for time. Some of the stuff that I actually had to do is I was asked to basically revive an assay that the original paper on it was from the 1970s, and it used chemicals that had unfortunate names that I won't repeat because they're very, very dated, and also a bunch of very bad acids that are ungood on robots, to say the very least. And so we actually had to go and completely modernize a very old assay, and we were able to do that. So assay modernization is not trivial. The only reason why we looked at this assay is because there wasn't really a modernized version of it. And the last thing that's in kind of our regular development is we end up 3D printing a lot of stuff because it is such a quick solution to small lab problems, and it doesn't require us to hire an incredibly expensive engineering firm. And we build it in-house. We know what we got. We iteratively build and rebuild. So that's kind of what a day-to-day looks like for us in engineering biology. But with what I said about people come to us in Saskatoon with weird problems, it's never really, can you just take A to B to C? There's a bunch of exceptions. And so we do the weird things, and our service requests match that. And very early on when I started this job, I realized I would need to get good at developing things quickly and in a very strong troubleshooting background. And my background was basically all I ever saw was trouble. I took on assays people really didn't want to deal with and figured out how to get them to move forward. And so, like I said, the question is how to look at this kind of mess of what can come up and how to get through it quickly and in an ordered way. So I made a very quick mindset. Saskatchewan kind of prides itself on this pioneering culture. And so my role is pretty similar to that. I take a lot of things from absolutely nothing exists on it to some kind of minimum model. We call that an MVP, a minimum viable product. But the first step you have to do in building any of these complicated assays is you have to minimize all of the complexity and try to make it as straightforward as possible. Sounds pretty obvious once you've done it enough, but I think sometimes people, when they're looking at this, they want to retain a lot of complexity in initial designs, and it just doesn't work out. I took a great quote. One of my biggest personal interests is basically the last two world wars. So I took a quote from the Red Baron, if nobody recognizes that name, which is focus on shooting down the enemy. Everything else is nonsense. So an assay has a singular goal. Focusing on that goal and dilating in to get at least one successful metric for a lot of assays is the starting step, especially if you're encountering a lot of hurdles. These are some of my very, very simple trivial fixes. So some of the users weren't quite sure what the positions on the deck were. I printed off a map. That's kind of the top two images. The bottom one, Mike Saul might have a comment on this. The Hamilton heater coolers that we got, it takes them about 28 minutes to cool down to 4 Celsius. We needed that for the start of an assay. I decided I wasn't going to try to start the robot 28 minutes later. I was just going to take a 96 well plate, fill it full of water, throw it into -80, and use it as an, in quotes, cryo battery to rapidly cool the thing down. This is one of my favorite examples of a stupid fix is way better and way faster than a smart fix. So I saved about 24 minutes in cooling down that unit every time we do this assay. Anyone who's used an automated robot, there's a lot of checks and balances you can put in to stop users from putting stuff in the wrong place. I've taken out some of the safeties because I found it just makes the machine run slower, and then the users end up being less familiar with the machine. And instead, the 50, 1,000, and 300, those are tip sizes that go in those columns. So this is one of my best examples of stupid is fast, smart is slow. I don't have to do a bunch of security checks on my users. They have to get familiar with the machines. They have to know exactly what the machine's going to do, and just putting a label on it forces them to learn it. Uh, this is my favorite one because I it's so weird. With the other automation engineer I work with, there's basically only two in all of Saskatchewan that are actually coding. She was doing all these tips and tricks for how to figure out how her pipetting and dispensing was going. You want the tips to get to the bottom of the well in the plate, and she was kind of tilting it and doing all these other things to see if it would jiggle. I just took a pair of tin snips and I cut the sides off to see if it would go to the bottom. It's not rocket science, but now I know exactly how all the liquids were performing. This actually allowed me to dial in a bunch of liquid classes for weird things like glycerol because I could see it actually needed an extra 20 seconds, but an extra 3 or 4 seconds before you can dispense it. And this is the kind of thing where when you wonder why you're short a couple microliters at the end of an assay, having a tool of just a plate with its side cut out and repeating it will tell you exactly where that's coming up short. The other thing that I'm a big advocate of, and I know in a lot of regulatory environments you have to live completely off SOPs, is not having them within reach of my robot because it doesn't seem to help anybody. We had some people who would come and pursue something on the robot. Something would go wrong, and they would be in enough of a panic because it's not a cheap robot that they would try to rapidly fix it on their own. And somebody had said to me, "Oh, it's going to be fine. It's in the SOP." And I'm like, "No, no, no. You don't get it. You're going to panic because what's going to be caught in the tips is something you can't lose." And what you need is a solution that's within reach. So one of my rules for robotics in the lab is if it's not within reach, it doesn't exist. So all of your solutions for if something goes wrong, it should be very, very close by. No one in a time crunch will ever consult an SOP, especially if the liquid's in the tips and it's already dripping out, something's crashed. It's happened. I've seen that happen twice now with irreplaceable samples. The other half, embracing the weird. I hate doing the same thing twice, so I'd rather make it once, make it good, make it universal, and then use it everywhere. I was able to kind of steal a great Carl Sagan quote here, which is, if you want to make an apple pie from scratch, first you have to create the universe. So this was kind of the mindset I was operating on, where I wanted to build a universe where I could quickly do anything I wanted to do in the lab and on the robots. But that was the big time hurdle. I had to develop that environment very methodically. And after that, it was trivial to make an apple pie. It's completely easy compared to the universe. And when we're doing routine stuff, and so one of the natures of my platform is that we're constantly asked to use our robots to solve the problems, but we're never really using the exact same method. And so I needed to be able to make a brand new method very, very, very quickly, sometimes the day that I was asked to do it. And we've been able to do that successfully now quite a few times. And one of the other great things here is creating this environment to do things quickly also let me lower the amount of intellectual energy and my time that went in. And also by making these generalized steps, we have steps that just don't fail anymore, which is very comforting when you're designing code and passing it to somebody and you're not able there to supervise its first testing. Well, Mike Saul here will be very familiar with this, but I'm just breaking down the structure of anyone who's not familiar with automation coding. You're kind of going to get this format on the left. You've got an initialization, you've got a core method, you've got a shutdown. It had been very routinized from what I'd seen that people didn't have a universal initialization. So every time they initialized, different parts of the robot would be turned on and be set and ready to go. But if they wanted to change something downstream, they had to go back and add some components to that. I decided that was a bit silly and redundant, so I just made all of my robots have the exact same startup. They just turn absolutely everything on, unless it's a part that takes a long time to start up. And then I have a bypass for it. Same with the shutdown, same with the abort. When the robot shuts down, it shuts down everything it's turned on. It's not rocket science, but when you're designing a lot of methods very quickly, being able to copy and paste about 90% of your code to get rolling is a big time saver. I don't know how many people in this room are actually coding any form of robot regularly, but Hamilton's specifically come with, you get a deck layout that you can define on there. The automation engineer that first kind of showed me what they were doing, they had a deck layout per method. Each one of these has to be trained in, dialed in. Every time you get a PM, you're going to have to redial stuff in. That's too much work for me. I made one deck. It does everything. It serves 61 methods. I've had 0 errors. This might be apocryphal to Hamilton's mindset, but I'm open to that judgment. It's reducing redundancy as part of Lean Six Sigma, which is why I've got the little symbol there. There we go. So this is the mentality I kind of came through it with my first couple of years, throwing really hard into this robotic development, which is keep it simple, test a basic model. Users and other scientists in the lab, they're always going to ask you for way more than they actually need. And reducing it back to a basic model and then testing it to make sure they're happy with the assay as it is a great place to start. And then you evolve to what's actually needed. We overbuilt some stuff in the beginning, and then I ended up kind of just undoing it back to a basic model. And so I decided to just skip the middleman and just go for the easy route first. So with this mentality, I did need these systems challenged. So this is timing it to about 3-ish years ago, when I first started. And I specifically, very important thing if you're new to getting into robotics is you should definitely monitor what your problems are, what source they're coming from. 5 minutes. I think I should be able to get her. So that was the best first step I made. So this is just highlighting the single first week that I was coding and getting some stuff running. I think it was 31 out of 34 of my errors that caused a method to stop were from poor copy pasting and very, very small errors. Anyone that codes copy paste is like a god in computer science. You just do it and you do it for everything, and that solves a lot of problems. So what I ended up having to do is instead of copying and pasting these kind of bigger, kind of obtuse, hard to read lines of code, I had to simplify everything into functions with very, very simple calls. I was told for IP reasons, I'm not allowed to show that much of my coding environment. I was going to show quite a bit of it, so it's a good thing they said something. But I also kind of compartmentalize anything. Anybody who's ever coded on a lab robot knows there'll be kind of a listing of these drop-down options or coding settings, but it's kind of scattered. I just centralize them just to make it a bit quicker. There we go. So what failed next? These are the other lovely people that I work with. That's Matt on the left and then Tongbo's on the right there. The next biggest error we kept getting was just user interface. I wasn't writing clear instructions for what to do on the robot. Code was good. UI was bad. The robot's expensive. They were both nervous. That's fine. It was an easy fix. I built a minimal UI. We moved on from it, but it was important to get the robot running. I knew the worse the UI was, the more they'd have to learn the robot. And so it was kind of a self-incentive to reduce their own constant daily fear. And that's maybe not the best way to teach somebody, but that's what I chose to do. So this goes all the way back to the start. So I won't break down the names of this. So AET is a method. The very first one I designed. It took me roughly 1,400 minutes to do the first draft. It was an extraordinarily complicated method, but coding anything on a robot, you really want to check all your safety. So this took a very, very long time. The key point here is as I started applying this mentality, I eventually decided I was just going to remake that method, the very first method I made, to see how long it would take me. It took me 7 minutes to entirely rewrite the first method. The method runs for about 2 hours. It's got like 11 pipetting steps. It moves plates on incubators. It runs timers. It does all of the kind of basic stuff you do in automation. Incredibly trivial to reprogram after I had built what we call in-house the Pickering system, which I narcissistically named after myself because I didn't have a better name. But it's got a different name on the Vantage. But yeah, so I made this, and then I needed this as a place to measure how far we'd come. Then we got a bunch of projects from clients. I started making some stuff very quickly, and then we got to the newest thing, something we called the GC project. We had to make a ton of stuff for that. If I was developing the same rate I was at the start, there's no chance we would have made it on time because it was 12 full methods, and we knocked those out very, very quickly because we had figured out how to standardize these parts, make everything very simple, test the basic model, and just move on. But the highlight here actually is the biggest slowdown once you get kind of these smarter systems going is the artisanal cases and the weird liquids. And handling glycerol or a mix of glycerol or a shifting mix of glycerol and water, it's tricky. And when you want to be microliter accurate, that's a hope and a prayer a lot of time. So you do what you can. The other big benefit of me making a much abbreviated coding system is that all of my users are able to go and one of them doesn't code. The other one codes enough to be dangerous. Was able to use my functions basically, which each of them contain 20 to 70 lines of code. I think one of them is actually like 400. But it's a single line call. They fill in a couple variables. They get their action. The plate goes to the incubator, does the incubation for an hour. It comes back. It gets pipetted onto. I can read the code very easily. They can edit it very easily. And this meant that when I asked Tongbo to code something, she was able to code the method that she needed in 3 hours, and she'd never coded before in her life. Um, there were a few typos, which were her fault. There were some mistakes that were my fault, but after fixing the minor errors, it worked. So I can't speak to other automation engineers labs for if their included members can do this kind of thing. I think I'm just about at the end here. 1 minute. So this is just a highlight. Whenever you're doing anything in robotics, you kind of have four main stages: coding, mechanical testing, water testing, real testing. All the first three stages massively reduced by the fact that I'm essentially using very intelligently copy-pasted code of very readable, human readable functions. Just going to move on from that so I can get this done in a minute. This is how I live. I write everything kind of on paper first. I kept a slide in to show I didn't need a fancy graphic. I put a bad image in here to remind me to make something slightly nicer. So a lot of my solution in the end here is I didn't need a fancy coffee maker. I just needed a coffee maker. Or in this case, I didn't need a fancy science maker. I just needed a science maker that worked reliably. And so that's our Hamilton star. The first image on here of it is very, very clean. You can see this is basically now a crescent moon of me putting Post-its and everything everywhere. And those Post-its are all the technical details about tiny little things that we've done in all the error testing. So when stuff goes wrong, if something's out of spec, we very quickly test. And you don't need to close and open the UI on anything. It's physically available and reachable. Two people today mentioned the KISS principle to me, which is keep it simple, stupid. Amazing engineering concept. Don't overcomplicate stuff. But if you are looking to increase your methodologies for efficiency, Kanban, Lean Six Sigma, Kaizen, amazing things to have. And two of my main things here, I think I cut out my slide that used to say stupid is fast, smart is slow. You can't always be smart and fast. You pick one or the other. You can either have a complicated method, you can have a simple method, you can deploy it quickly and iterate on it quickly. And standardize. Don't change the chessboard when you're building a lot of stuff. Just keep as much the same as you can, because your brain is not going to store it very well. And this is my Hamilton advantage. And the powerful thing that we did here, part of a design, build, test, learn cycle, everything you see in blue is something we 3D printed to augment the machine. We've taken its base capacity up with the blue slots in the back line to 35 plates. We've got an exit entry on it that helps us get up to, I think, about a 35 tip rack capacity. We've got our 9 incubators on deck there. We can even freeze stuff on deck theoretically. And the weird blue things you might be able to see on the side there. That I added on because when we put there's units beside it that are silver. We didn't have enough room to put anything else in that little slot. So I had Matt 3D print these, what do you call it, portrait landscape lid holders. And so now I got an extra 15 lid holder positions from the space that's empty. So I'm not wasting any real estate here, this is a good audience to talk to about real estate prices. Houses are pretty cheap in Saskatoon. They're not so cheap here, I'm told. But I'm not going to waste a single square inch on this machine. And we were able to fully onboard this just mere months after install, which was a very obsessive task of mine. Yeah, just some 3D printed examples, but we can jump to questions here. One quick question. I hope it's weird.
Thanks, Josh. Was very interesting. Great talk. So when you talk about the Pickering method, it's basically you've implemented your key steps and stored them in SMT, right? SMTs, the sub-method technique.
Yeah.
So then you have your library of take that plate, move it from A to B or to incubator, and the user can drag, drop, and fill in the variables. Is that correct?
Yeah. If you're deep enough in the woods here and you're familiar with PyLab Robot and kind of the mentality they have, I've discovered weeks after I kind of assembled this so that I can call in any action I want with just a couple clicks. They made kind of a better UI for how to interact with PyLab Robot, and it was very similar to what I had made. And then a Hamilton engineer passed me a bit of code, and somebody at Hamilton had made something very similar. Not quite as good for my users as what I made, but the mentality is there. I think other people are developing it, but when I've gone out and seen other people's code, they're still every single time they're fully building out the code. They're not making these quick callbacks.
Yeah, because that's one of the approaches that I wanted to take. But the question was, even if I'm doing those SMTs, users still have to populate the variables when you put your
Yeah.
drag and drop. So is it hard for them in your with your what you
Well,
observed?
I think sometimes a limitation is a great thing, and that when you don't give them another option, they learn that they have to learn.
Mhm.
And so I was lucky that one of my users is a coder, but the other one isn't. And there's no fear. I taught her what variables were within about a week. She was coding her own variables. She's making her own little chunks of UI so she can change the pipetting height on her control and all that kind of thing. But it's just about taking away the hardest steps, because the hardest steps is all the expanded. I don't know what you're coding in, if you're coding in Venus, but there's so many drop down menus. There's so many options. There's so many
Yep.
everything. Taking away all those options didn't make us weaker. It made us faster. And for us, that was just critical. And a lot of times those options were where the copy paste mistakes were in the first place.
Okay. And sorry.
Okay, we're running a little bit behind here, so we're just gonna have to wrap that up. Maybe you guys can touch base here during the coffee. So we've got coffee out there for everybody. Please vote for your posters and please come back here at 3:10 for the last session, okay?